Hello everyone, my name is Hongxiang. I'm a third-year PhD student at Imperial College London. Today I'm going to present my paper, Optimizing FPGA-Based CNN Accelerator using Differentiable Neural Architecture Search. Our contribution includes, firstly, we propose an FPGA-based CNN accelerator with high resource efficiency. Secondly, we propose an accurate hardware performance model to speed up the performance estimation. Thirdly, we apply the hardware-aware differentiable neural architecture search to achieve high hardware performance as well as accuracy on the proposed FPGA-based CNN accelerator. Now, let's start from our hardware design. The system overview is presented in the slide. The host processor is used to set some hyperparameters of the whole system, including the number of channels and the number of filters. The intermediate results and the weights are stored in the off-chip memory. The FPGA system is used to perform the main computation of CNNs. To save resources, we run multiple convolutional layers on one processing engine, so the core module in our hardware design is function unit, which is used to perform the convolution, batch normalization, pooling, and shortcut. Based on the hardware design, now we introduce our performance model, which includes loading time, storing time, and computation time. The loading time means the time spent on loading inputs and weights from off-chip memory to on-chip memory, divided by the efficient I/O bandwidth. The similar formulation can be applied on storing time, which divides the amount of output data by the efficient I/O bandwidth. The last term is computation time, which is dominated by the amount of computation. Based on the proposed hardware design and the hardware performance model, now we introduce the neural architecture search for FPGA. An overview is illustrated in the slide. The search and the training are performed on GPU platform. The performance model is used for the fast performance estimation. The found neural network will be deployed on the proposed CNN accelerator at the end of the whole process. The microarchitecture of the search space is presented in the slides. The AnyNet block is a basic block in RegNet, which is a searchable cell in our paper. It's composed of a standard convolution followed by a group convolution with shortcut enabled. The domain for the kernel size and the group convolution is also presented in the table on slides. Now we introduce our experimental part. The hardware design is implemented on Intel Arena 10SX660 platform using Verilog. The quarters is used for synthesis and the clock frequency is 220 MHz. CIVA10 is used as our dataset with 10 classes for classification. Firstly, we test the accuracy of the performance model on VGG16, ResNet 50, and Inception. The result is illustrated on the table. The prediction error is less than 5% on these three models, so it's accurate enough for estimating the hardware performance. Next, we compare our method with the existing work based on the reinforcement learning-based neural architecture search. We can improve the accuracy by nearly 10% while reducing the searching time from 108,000 to 25 GPU hours. So our future work includes validating our proposed method on the larger dataset such as ImageNet, integrating quantization and its effect into our neural architecture search framework, and improving the search strategies to reduce the search cost. So this is my presentation. If you have any question, please ask the question during the Q&A slide session or just email me. Thank you.